Hello everyone, it's a pleasure to introduce our work here. My name is Fengliang. All four of our authors are from the School of Software Engineering, University of Science and Technology of China. The theme of our work is simple contrastive learning of graph embeddings for classification binary code similarity detection. A single bug at source code may propagate to hundreds or more devices with different hardware architectures and software platforms. In face of increasingly complex computer security series, security practitioners are increasingly demanding the ability to detect cross-version binary code similarity. But the binary code similarity detection has many applications in the field of software security, such as software plagiarism detection, malware analysis, virus detection. Improvement of BCSD capabilities is an urgent need in the security field. Shown in the figure, this is the architecture diagram of Siamese network. Most of previous related work adopt the Siamese network architecture. In the experiment, we found that it is prone to overfitting, and it is insufficient consideration to mark the similarity of function pairs with the same source as 1 and those with different source as -1. For example, when two binary function pairs from different sources are very similar, it will introduce a lot of area information to the model. Such a simple architecture cannot fully utilize the representation ability of deep learning models for contrastive graphs. Germany is the classical method of BCSD because he first proposed a Siamese network and used artificial method to construct node features in contrastive graph, and finally obtained the representation of binary functions through a simple graph neural network. The left picture is some artificially extracted features of graph nodes, which include string constants, numerical constants, number of instructions, etc. The right picture is a semantic diagram of artificially extracted features for the contrastive graph. Due to the emergence of various graph neural networks, we also have more options for contrastive graph. As shown above, PNA, which was proposed last year, shows how a node extracts information from its neighbors. Each node captures different types of messages from neighboring nodes with 4 aggregate and then goes through 3 scalars to obtain 12 different representations of the original node as the node representation after obtaining the information. As shown on the left, it is a schematic diagram of contrastive learning. It aims to learn varied representations together with pushing away non-neighbors by drawing thematically close to them. The key to contrastive learning is constructing positive example pairs. On the right is a mathematical expressions for contrastive learning, which hope that the higher the similarity of positive examples, the better, and the similarity of negative samples, the lower the better. There are 4 main contributions in this paper. First, we propose a novel framework for extracting CFG embeddings. Second, in the CFG representation, we extract CFG embeddings by PNA. Third, we introduce contrastive learning into the graph representations. Fourth, we conducted experiment on 3 datasets, and the results show that our proposed approach achieved better performance than previous. The input data for our model is CFG of the binary code decomposed by IDA Pro. The overall architecture is shown in the figure. In the semantic extraction part, we use a BERT model with two pre-training tasks to extract the future of the basic blocks. In the structure extraction part, we use a PNA with multiple aggregate to extract the future and the structure embedding of the graph. For the training architecture, we follow the contrastive framework and use an embedded negative cross-entropy objective. In this paper, we pre-trained BERT using two classical tasks for BERT pre-training, MLM and ASP. The corpus is a collection of basic blocks of each version of the CFG, and treats each basic block as a sentence and two basic blocks with edge as a consecutive sentence. Our vocabulary consists of about 19 mirror-code instructions. Because our vocabulary is small, we embed each token as a 129th dimensional vector instead of 769, and accordingly, we shrink our hidden layer to 1024 dimensional 12-layer transform structure. In the MLM task, we mask the 12% of the token for training. In the ASP task, we took two blocks of each edge as consecutive sentence and an attribute edges in the block set for the starting blocks of each edge to train as a negative sample. Finally, we take the average of all tokens in the last layer of BERT as the embedding of the blocks. The figure is a diagram of the embedded negative example, which treats all non-positive examples within the same batch as negative examples. After computing the similarity, it is similar to a classification problem with the first column in one class and the others in another. The key to contrastive learning is to obtain the corresponding anchor and positive. In BCSD, each version of the binary function anchor is naturally the positive of the corresponding function in the other version, which fits perfectly with the idea of contrastive learning. Compared to Siamese approach of pulling positive, pushing negative separately, it is more reasonable to contrastive learning, pull positive considering negative and push negative considering positive simultaneously. We train the model on DNU debug and evaluate it on three publicly available datasets: Open, SSLF version, U version, and BZBox, with the same source code compared into different versions of the binary code, and compiled into CFG using IDA Pro. In a high-dimensional space, our goal is to push embedding of anchor and positive close together and to break up embedding of anchor and negative. Our version of the binary code including cross-platform, cross-compiler, cross-optimizer, and cross-bit. We have done extensive experiments on these different computational versions. This task of BCSD is similar to the recommendation system. Thus, we evaluate the model by MRR and recall at K. MRR is used for evaluating ranking tasks, which use the multiplicative inverse of the rank of the first correct answer. Recall at K means whether the ranking of the two pair is in the top K scores of the highest. And the baseline Gemini use structure to vector to compute graph embeddings of CFGs, where each block is an 8-dimensional manual select feature trained by using the same Siamese architecture. Semantic array is bad for task, and MPN and 11 resonant layer at Siamese, which contains semantic aware modeling, structure aware modeling, and sequential aware modeling. As our model is cross-version specific and Gemini Gemini as well as semantic array is cross-architecture specific. It is included in cross-version. We did a two-part comparison, taking the cross-architecture part out to compare with Gemini and semantic array, and then we focused on comparing Siamese with SimCGE in the cross-version part. In cross-architecture comparison, our model improves significantly more at all three optimized levels. We can see from all three models that the task at all three levels is relatively more difficult. But in our model, the difference between O3 and O2 is small. We think that this is because the Siamese trained model embedding is not uniformly distributed, resulting in sufficient robustness of the model. In the cross-version comparison, we compared various graph-neutral networks in Siamese and SimCGE. We can see that PNA has the best performance, followed by MPNN and voiced by GAT. Among the various genes, SimCGE outperforms Siamese. We have specifically analyzed the reason why SimCGE outperforms Siamese, as is shown in the right figure, where the uniform of SimCGE is much better than Siamese. The SimCGE's trained model allows for a more uniform distribution of CFG embeddings, although at the expense of a bit of alignment. Overall, it is easy to find positive for each anchor. In this paper, we proposed a novel training framework for binary code similarity detection, which consists of three parts: semantic extraction, structural information extraction, and contrastive learning. For the semantic extraction part, we use BERT with two pre-training tasks. For the structural information extraction part, we use PNA and contrastive learning instead of traditional Siamese architecture. The experiments were carried out with three datasets and showed that contrastive learning significantly outperformed Siamese, with PNA best extracting structural information from contraflow graphs. That's all. Thank you.